Robots are cool, but despite all the AI hype around, they are very literally minded. Robots will do exactly what you tell them to do, so you better tell them everything. This is a problem when what you want is a robot acting autonomously in an environment that is less controlled and more unpredictable than an assembly line. Therefore, it is a problem when what you want is a robot helper working along humans in human environments. One can get away with telling a robot to simply follow a scripted sequence of movements if the environment of the robot is relatively simple and tightly controlled. Do that for a robot working in the kitchen, and even the simplest tasks become surprisingly error-prone. You could give a robot a script to cook popcorn, only to see it drop the lid it should have covered the pot with, and then just stand around waiting while the heated popcorn jumps out and lands all over the floor. This seems an easy problem to fix. We just need to program the robot to check that it has placed the lid on the pot, and retry if it hasn't. But then sometimes the drawer will not open, or the pot slides off the hotspot, or the freshly cooked popcorn drops to the floor. The problem is not that the program becomes ever more complicated. A robot is a complicated thing. But each patch we added is very specific towards fixing a particular error and tells the robot little that would be of use somewhere else. In other words, these patches address symptoms, but not an underlying deficiency. The robot doesn't understand the causal structure of the world, nor the possibilities of interaction afforded by an environment, so it cannot use such knowledge to detect and repair failures as such failures arise. This is not an easy problem to fix. In its full generality, it is known as common sense reasoning, and it is one of the main interest points in current AI research. Any intelligent agent that acts in the world must, in some sense, understand that world and the consequences of actions taken in that world. At the same time, providing some computational implementation of common sense is very difficult, because even we human beings don't know how we do it. It comes too naturally for us. The big problem of common sense remains therefore open, but we have taken some steps along the way towards a computational model of a naive understanding of physics, which we will show you in this presentation. Specifically, we have implemented a computational model to understand what cognitive linguists call functional relations between objects, relations such as containment or support. These are relations that impose constraints on expected object behavior, and we will show how our approach enables causal understanding of the world and of interaction possibilities between objects in the environment. Such interaction possibilities are known in cognitive science and AI as affordances. We argue that when programming a robot so that it can face an uncontrolled environment, it is not only important to tell the robot what to do or how to do it, it is also important to give it knowledge about what can happen and why. Less script programming and more affordance-based programming. But first, some context. Since what we want is to encode some kind of common sense understanding of physics into a computer, it is only natural to use computational models for this purpose. That is, it is natural to use physics engines. However, researchers such as Ernest Davis and Gary Marcus have provided an extensive list of critiques of simulators as a reasoning tool. Simulators need physical models, and there may be no good implementations available for phenomena of interest. Simulators are often unstable and require hand-tuning to reproduce realistic results. There will always be a simulation to reality difference, and that puts into question just how much one can learn from simulating physical phenomena. And in any case, the more accurate, the more computationally expensive the simulation will be. These criticisms are true, though in these regards simulators are only getting better. However, Davis and Marcus draw attention to another, more fundamental kind of issue. Suppose, in preparation for a trip abroad, we put several clothes in a suitcase which we then drop at the airport check-in. We don't know exactly how the suitcase moved between when we dropped it and when we pick it up at our destination. We have no idea how our clothes moved in the suitcase. Even so, we expect to find our clothes inside the suitcase when we arrive. Reasoning from simulation cannot possibly have produced this expectation, however. Simulators need exact data about how a world is set up and what forces might be acting on its objects, and we know too little about the movements of the clothes and suitcase to be able to run any simulation. Instead, Davis and Marcus propose a logical theory to account for what it means for an object to be contained in another. In this way, one might have a principle, such as objects inside a container stay in that container, a very abstract and therefore very general formula that will not care about irrelevant details such as how the suitcase moved. The problem we see with a purely logical approach, however, is that it has a very hard time accounting for relevant details about the suitcase and indeed about the movement of the suitcase. Suppose we took it as a logical principle that objects in the suitcase will stay in the suitcase. But what if the suitcase has holes? But what if the holes are small? But what if the objects are very, very fluid? We see that a problem appears, similar to the one we encountered with the script-following robot. We can keep patching our logical representation of containers, but ultimately we need a model of how objects interact with each other based on their geometry and physical properties. In other words, either our patches to the logical system grow into a Byzantine mess, or we implement and use a physics engine to reason about physical objects. The two approaches, logical reasoning and simulator, cannot handle naive physics understanding alone. Combining them, however, is not straightforward. Logical principles as proposed by Davis and Marcus are useful because they are abstract and general. Simulators are useful because they compactly encode knowledge about which specific details of objects are relevant for a situation. We attempt to unite these divergent approaches using another concept from cognitive science, image schemas. These are intended to be cognitive building blocks human beings use to organize and make sense of experience. They can, and in recent years have to some extent been, formalized in a logical theory. At the same time, however, the notion of image schema is thoroughly rooted in embodiment, in perception procedures to recognize an instance of an image schema in the world, and in actions that would instantiate it. Image schemas have guided us towards creating a hierarchy of levels of abstraction at which to describe the world, and this hierarchy informs how we can bring together a very general, logic-based system and a simulator into a hybrid inference system. Also, the inventories of image schemas proposed by cognitive science researchers are finite. There is hope that at some point, maybe not too far in the future, we could have computational implementations for all of them. Unlike the program patching we saw earlier, there is some kind of end in sight, and every new image schema adds a lot of general knowledge. The most abstract level of description we consider is that of functional relations such as containment, support, or blockage. These are relations that, if they hold, impose constraints on the behavior of objects. We call these constraints expectations, and they are the defining elements of a functional relation. For example, we say that an object is supported if that object does not fall. Usually, an expectation is a qualitative description of a simple movement, such as nearing, distancing, or staying put. However, we also acknowledge a few special expectations, such as whether a path exists or not between locations in space. When motion data becomes available from a simulator, it will be checked against these expectations. Functional relations occur as an interaction between objects. An object is supported by another. To understand what is going on, it is important to take into account what we expect to happen when some object in the world were removed. If we took the support away, the supported object falls. If we took some unrelated object away, the supported object should stay put. For this reason, we say that expectations are conditional on an object, on whether it is present in a scene or not, and expectations where the condition is the absence of some object are called counterfactual. Counterfactual expectations are useful both to test whether an object actually does the work some functional relation claims it does, and more generally, as we will show later, to understand a notion of causality. we will treat what expectations are associated to a functional relation as innate and fixed. Functional relations, however, also include qualitative information about how to arrange objects so that, hopefully, the functional relation is achieved. As human beings, we already know several such arrangements. For support, we often convey them by the preposition on. For containment, by the preposition in. This is on. This is also on. This is in. And so is this. Therefore, there are default and then more particular ways, depending on object types, to arrange objects such that, hopefully, a functional relation is obtained, and our logical theories for functional relations are extendable with new such candidate arrangements. We will return to how these candidate arrangements are described, but first we must mention a particularity of our logical formalism at this abstract level of functional relations. It is non-monotonic and defeasible. That is, it is such that new data may invalidate old conclusions. We human beings have a tendency to overgeneralize. We see a bird for the first time, it flies, therefore we conclude all birds can fly. We learn afterwards this is not quite so. Still, we maintain as a default inference that a bird can fly, unless perhaps it is of a certain species, or sick, or in other ways exceptional. This overgeneralization is, in our view, a feature. We want our hybrid inference system to draw conclusions from a few simulation runs, conclusions such as whether a candidate arrangement of objects actually achieves a functional relation in general. These conclusions will be premature, but when the system encounters simulated situations where its conclusions do not hold, it can, by itself, add the qualitative differences to the original situation as exceptions in a more principled manner. To describe spatial arrangements of objects, we use qualitative spatial relations such as axis alignment, surface containment, point containment, and so on. Though very different, all such constraints can be uniformly treated as affecting a probability distribution over relative object poses. That is, given a grid of possible poses of an object relative to another, each such possible pose gets a weight according to how well it respects a set of spatial relations. For example, a typical way to support a cup on a table is to place the cup such that its bottom is entirely over the table and the cup will usually be upright. One of the basic questions we can ask is whether some functional relations will actually hold between a collection of objects if we arrange them in a certain way. Will cooking popcorn stay inside an uncovered pot? Turns out the answer is no. If we want the popcorn to stay in, we need to do something else. A lid placed over the pot will keep the popcorn in just fine. The physical characteristics of the objects are important, however. The popcorn might push off a very lightweight balsa board. Such what-if questions are useful when the robot wants to know what could happen with a bunch of objects and whether this outcome will match some desired specification. Obviously, this is also useful when selecting an object to achieve some task. We can even go one step further. We can ask why something happened. Let us return to the example of the pot of cooking popcorn covered by a lightweight balsa board. Someone has placed a cup such that it is supported by the balsa board. This time, the popcorn doesn't fly away. Why? Again, this seems very easy to us human beings, but to implement this on a machine, we must make the reasoning chain explicit. Let's look then in some detail at what causation could mean. Following the work of Judea Pearl, we treat causality in an interventionist manner. X is a cause of Y if Y will change because of a modification, an intervention, that we applied to X only. Specifically, what this means for our inference system is that it must test what would happen if it changed the scene such that one of the objects wasn't there. that it were a ghost which couldn't influence the behavior of other objects. In this example, if the cup weren't there, the popcorn would fly out of the pot. If the board weren't there, the cup would fall into the pot, and the popcorn would fly out still. This allows our system to blame, or credit in this case, both the balsa board and the cup together as causes contributing to the fulfillment of the expectation of containment. Note that this is a new conclusion. It is not necessary to assert in the initial qualitative description of the scene that the cup or the board contribute to the containment relation between popcorn and pot. Their contribution is inferred based on physical grounds, interpreting the results of simulation both of the initial scene and of counterfactual modifications to it. Much work remains to be done, of course. We have yet to formally treat several image schemas, functional relations, and the expectations they entail. Outsourcing some of this work to the greater public is an attractive option. Our colleagues in the sister project HO2 of the EASE Collaborative Research Center have looked at games with a purpose to elicit common-sense knowledge from humans about how to perform a task. Such games could be used to ask people about the large variety of candidate arrangements for functional relations. How would you place a poster such that it is on a table, or on a wall, or on a lamp? Acquiring simple response rules is another direction we intend to pursue. By and large, planning is expensive, and it is more plausible that as human beings we acquire a repertoire of stereotypical answers to stereotypical situations. Something gets out of a container and you don't want it to? Then place another object to block the exit. This is an example of such a simple and very general response rule, expressible in the vocabulary of functional relations, spatial arrangements, and expectations that our hybrid inference system handles. Reasoning about which such rule is applicable in a particular situation, or how it should be specialized to the available objects, is the next step towards an affordance-based programming that would make robots better able to cope with the many possibilities of the real world. For more information, you can find us at the University of Bremen in the Linguistics and Digital Media departments. We will happily answer your questions, either in the upcoming Q&A session or later via email, and we wish you a stimulating rest of the conference.